Okay, thank you all so much for coming today. Really excited to see you all, and even more excited that there are clear skies out there. Usually we have horrible luck, and every time we have a lecture, it is cloudy. Last time we had a lecture during the day, we wanted to see the sun. There was one cloud in the sky, and it was in front of the sun the entire time. So we're very happy to have clear skies and you all today. We have a wonderful talk planned for you. I'm very excited to learn as well. So as always, we'll start with trivia. We'll give some announcements. Then you'll hear our fabulous speaker give her talk. We'll do some Q&A, and then we'll go outside to observe. No question mark there. We're definitely doing it this time. Okay, so trivia. The way this works is there are 5 questions, theoretically in easiest to hardest order, but I'm the one sorting them, so you can disagree with me. I'll give you some time to think about it. Feel free to chat with folks around you. You don't have to keep your thoughts to yourself, and then we'll vote on it. So if you think the answer is A, you'll show 1 finger, B is 2, 3 is C, 4 is D. This is just so we can see if there's any kind of consensus throughout the room. Your first question. How many stars is the Milky Way believed to contain? So this one requires a little bit more than astronomy knowledge. You've got to know the answers to these as well. But that's why it's fun being in a room with collective knowledge. Maybe some of you do know. So I'll give you about 10 more seconds to chat with people around you, and then I want to see what your answer is. I see some grad students in the audience with confused looks as well, so we're all in the same boat. Okay, 3, 2, 1, vote. All right, let's see. I'm seeing 5s, 2s, 1. Wow, maybe I don't see any 3s. I see a 4. Okay, I see 1 3. All right, so we officially have all of the answer choices. And the correct answer is D, the same number of trees in the Amazon rainforest. When I saw this, I had to double check it because I thought there's no way that's true, but it is. There are about 300 billion trees believed to be in the Amazon rainforest, and astronomers believe there's anywhere from 200 to 400 billion stars in the Milky Way. So it's kind of amazing. That gives you an idea of how dense the Amazon rainforest is. We squish a whole galaxy almost into just part of one country. All right, question 2. What is the most abundant element in the universe? So we're now skipping over into chemistry, which will be a part of the talk tonight. You'll get so much more background during the talk. But let's see what the prior knowledge is to begin with. We've already got some confidence answers. I'll give you all a little bit more time to chat and think. Okay, 3, 2, 1, votes. I'm seeing a lot of 1s. I'm seeing some 2s. We definitely have some consensus. And the answer is hydrogen. So hydrogen is the most abundant element. Most of it was formed during the Big Bang. So when you drink water, which is made of hydrogen and oxygen, the hydrogen is most likely to be 13.8 billion years old. So next time you take a sip of water, think about the journey that hydrogen has been on to get to your water. Okay, question 3. Which of these are not real elements on the periodic table? Hopefully the periodic table image is blurry enough that you can't read it and cheat. They all sound kind of fake to me. I'm hearing good discussion. Let's vote in 3, 2, 1. Okay, I'm seeing some 4s, some 1s, 3s, 2s. Okay, so we once again have quite a variety. I see a shrug. I was also thinking that myself. It's D. We don't have Manhattanum. So we do have elements that are named after different places. I'm sure the people who discovered them got to name them and picked them after probably wherever they were. All right, question 4. Which process powers our sun? Okay, let's vote in 3, 2, 1. I'm seeing 4s, I'm seeing 3s. Okay, I think I see mostly 4s, but a good number of 3s as well. And that is nuclear fusion. So fusion is things coming together. In this case, it's atoms coming together. If you squish atoms together, you can get a new atom or a new element on the periodic table. This gives off an extreme amount of energy. If we could do this on Earth, we would have energy for everyone. But unfortunately, it takes a lot of energy to be able to do this. So the technology on Earth is not powerful enough yet. People are trying it. Maybe one day we'll get there. But the sun is so massive that it does this very easily in the center. And when it does this, it can create new elements, which leads us to our last question. What is the heaviest element that can be produced through nuclear fusion? So what is the heaviest element that a star can produce? And these are all real elements, I promise. Okay, 3, 2, 1, vote. I'm seeing a lot of 2s. I'm seeing 1, 5. All right, I'm seeing some 1s as well. Our answer is iron. So that is not the heaviest element that's on our periodic table, but it is the heaviest one that can be made in stars. So that tells us that those other elements, the many other elements on the periodic table, must be made in different processes. All right. That's all for our trivia today. Thank you so much for playing along. It will be exciting to see how your knowledge grows. Our announcements is that this is our last lecture for the summer. Summer is ending. I've been talking to a lot of my colleagues about where did the summer go, but we will continue them in the fall. We don't have the exact schedule yet, but we will be posting it on the calendar on our outreach website, and we'll be sending out announcements always 2 weeks in advance. So thank you for your patience, but we're excited to continue this into the fall. And now we'll have our talk from Dr. Catherine Manea. Catherine is an NSF Astronomy and Astrophysics postdoctoral fellow at Columbia University. Her research focuses on stellar compositions to trace the origins of elements in the periodic table and examine how the Milky Way's chemical makeup has changed over time. She earned her PhD in astronomy from the University of Texas at Austin in 2024. Outside of research, she enjoys hiking, knitting, and walking her dog, Pepper. All right. Thank you, Catherine. Take it away.
Thank you. Can everyone hear me okay? Should I be a bit louder? A bit louder? Okay, maybe I can turn this up, or maybe I can just go like this. Hello? Hello? Thank you. Okay, how's this? Okay, good. Let me know if it gets too loud. Thank you so much for that wonderful introduction and the trivia. Oh, sorry. Okay. Great. Okay. Oh yeah, I have this. Good. You know what? Sorry. Hello. Great. Okay. Okay, good. We're here. Thank you so much for that amazing introduction and the trivia that was very relevant to the talk today. So today, yeah, Amanda asked if I'd like to give a talk in this series. And I said I would love to. And she said I can give it on anything. So I'm going to be giving it on our Milky Way and the ways we study stars to understand our Milky Way. So my topic of interest is, yeah, the Milky Way. And I'm curious about how it formed, how it's evolved, and how it's structured today. And this is a major open question among astronomers today, which is why we've invested so much money in building facilities to answer these exact questions. And in an ideal case, we could travel outside the Milky Way and view it from a bird's eye view. So we could study the Milky Way and travel through space and time to understand it in the past, turn it around, look at it from all these different angles. But unfortunately, we can't do that because we live here. We live in the Milky Way. We're embedded in the disk of the Milky Way. So, and just to be clear, so the Milky Way is called a spiral galaxy, which means it has a disk. It has these spiral arms. Ooh, sorry. I'm so sorry. Oh, there it is. I found the laser. Okay, sorry. um, It has these spiral arms, and yeah, we live here. So we can't escape the Milky Way yet to study it from an outsider's perspective. Instead, our view of the Milky Way looks something like this. So if you've ever stepped out in a dark sky area where there are minimal city lights and you've looked up, maybe it's the summer, you might have seen a patch, a streak across the sky that looks something like this, a light streak. This is our Milky Way, and you're peering into the center of our galaxy. So it took me a long time to actually understand this perspective. I don't know about you guys. But yeah, so we're in living in its disk, and now we're looking at its center right here. So this is called the galactic center. It houses a supermassive black hole that's swirling matter gas really rapidly, and it's emitting tons of light. That's why you see all this light over here. We can also see these dark patches that run across the Milky Way. This is dust. There is a ton of dust in the disk of the Milky Way, and this dust is critical for forming stars, and we'll talk about that in a second. Also, most exciting to me is the rest of the light that you see here all comes from stars. And stars are my favorite thing to think about and to study. And also, if you're curious, we see two little blobs down here. If you've ever been to the southern hemisphere and looked up in the night sky, you might see these blobs. I don't know if I can actually ask a question, or I don't know, does anyone know what they are? Yeah, good, excellent. So these are the Magellanic Clouds, the small one. And these are miniature satellite galaxies that are orbiting the Milky Way. Great. So because oh, by the way, I wanted to mention, this is an actual image of the Milky Way. This is not an artist's impression. This is a composite image from several observations of stars over many years from a satellite telescope called Gaia. Okay, but yeah, so if we want to answer these questions, we have to get pretty clever. So what can we do? Astronomers have come up with several clever ways to study the galaxy, even though we have these limitations of being embedded in it. A few of these examples, we can look outward. So let's forget about our Milky Way and let's look out away from it. So you might be familiar with the concept of when you look out and far away and at distant objects in the universe, you're actually looking at things as they appeared a long time ago, because the light that those objects emit takes a long time to reach us. For example, this team of astronomers at UT Austin, actually, they asked to point a space telescope called the JWST at this galaxy, which is super far away. And the image they got is of this galaxy as it was 11 billion years ago. So the light we're receiving from this galaxy is 11 billion years old. So we're kind of looking back in time. And what they noticed is that this galaxy kind of looks like our Milky Way. It has this bright center and these arms. So they are positing that this could be an ancient version of our own galaxy. Like maybe our Milky Way looked like that. So they use this and they study this image and they say, maybe that's what our galaxy looked like before. And we kind of can guess what it looks like now. Yeah. We can also look outward, but a bit closer by, and look at our neighbor galaxies that are spiral arm disk galaxies like our Milky Way, and study their structure from the outside. So we have this outside view. And this is an example of NGC 7773, which the point is it's a Milky Way-like galaxy, and its orientation happens to be such that it's what we call face onto us. And we can use big telescopes to study its structure. We can look at these bright patches that are newly forming stars. We can see its center. And we can guess that our Milky Way probably looks something like this. Another way we can try to understand our Milky Way is by not even bothering to look at anything at all and creating our galaxy in a computer by simulating it. So we start by getting a really expensive, powerful computer, and we put into it all of our knowledge of physics, and we let it go. And our computer will create little mini galaxies. I mean, not mini, normal size galaxies, but they're in a computer. And we can study all the versions of the galaxies that come out, and we can infer that our Milky Way probably looks like one of these things. And we can study it in detail because it's a simulation in our computer. So we can zoom in on one, understand everything about it. Finally, my favorite way to study the Milky Way is to actually look at it. We look inward and we directly study the Milky Way. But again, we're limited by this view that we have of being embedded in it. We can only see parts of it. We can't see the whole thing. So how can we get around that? We can study its stars. So stars are tools for probing the Milky Way. Their positions in the sky, their velocities, how they're moving around, how they're orbiting the center of the galaxy, and most important to me, their chemical compositions are imprinted with memories of our galaxy's past. And I'm going to explain that in a bit. But yeah, so my favorite way to study stars is through their chemical compositions. And this figure will make sense in a second, so just don't think about it too hard. And this method of using stars as tools for studying the Milky Way is called galactic archaeology. So it's the idea of treating stars as fossils that reveal things about our galaxy's past. And if you know anything about the term archaeology, you might be like, wait, hold on, you said that stars are being treated as fossils. Shouldn't we be calling this field galactic paleontology? Because galactic archaeology would imply that the Milky Way is like a culture and stars are humans, and or maybe they're pottery. Anyway, I agree, but we all ignore that and we still call it galactic archaeology. So yeah, okay, so then how does galactic archaeology work? Why can we use stellar chemistry to probe a past Milky Way? To understand that, we need to understand three things. How are elements created in our galaxy? How are they imprinted on a star? How do they make their way on a star so that we can study that star chemically? And finally, how do we even measure a star's chemical composition? So let's start with the first one. As you all know already, thanks to the trivia, chemical elements are created in stars and stellar explosions. So I'm showing a few examples of dramatic events that create elements. So not only do we have typical fusion that you guys were actually just talking about in the trivia, but we also have these massive explosions, supernovae. We also have stars turning into these things called nebulae or planetary nebulae. You might see, if you've ever looked at astronomy, images, one of the most popular and pretty image is of a nebula where you have this beautiful rainbow. So elements actually are created right before the nebula is ejected. So that nebula creates or releases new elements into the galaxy. We also have these really rare but highly energetic events that create elements called neutron star mergers. So this is the merging of two really dense stars that come together. They explode, they create several really heavy elements that are radioactive and very rare. And they also create something called gravitational waves that were first detected in 2017, and that is currently a huge topic of interest in the field. And so these events are going off all around the galaxy at all times. So the Milky Way's composition is changing because these events go off, elements are created, and then they enter the galaxy. And so if you might be familiar with the periodic table, maybe from school, maybe this is your job and you're a chemist. Hopefully not, because I'm definitely not a chemist. I'm just an astronomer and I use elements to tell me things. But you might be familiar with this. This is the periodic table, elements organized by atomic mass. If you are maybe a bit more into chemistry, you might be familiar with the periodic table colored like this, where you have categories such as the alkali metals, alkaline earth metals, halogens, noble gases, and so on. If you're a regular astronomer, you will look at the periodic table and see this. You'll see hydrogen and helium, which are two elements that were primarily created in the Big Bang, so the birth of the universe. And then everything else honestly doesn't matter that much because all of those elements are created in stars and they're called metals. So if there's any of an element, there's a metal in there. And in my field of galactic archaeology, when we look at the periodic table, this is what we see. So we see all of the elements painted by the event that creates them. So for example, let's look at magnesium over here. You can see that it's almost entirely orange-yellow. That means it is almost entirely created by exploding massive stars. So if you, or I'll get to that in a second. You can also see this element down here, europium, which is a real element, apparently. This element is primarily produced in merging neutron stars. Again, those really dense, weird stars that come together and then create these weird radioactive elements. Yeah, and so yeah, just to really bring this home, the iron, the calcium, the potassium on Earth, in your body, in our sun, was all created in stars that created these elements, and then eventually they made our way into our solar system and into our body. Great, so that's how elements are created. How are they imprinted on a star? So to understand that, we need to understand how stars form. So this is an artist's impression again of the Milky Way. Again, we can't exit the Milky Way. So any vision, any image you see like this is always an artist's impression. Stars form in what we call molecular clouds, which are dense pockets of gas and dust that lie within what we call the interstellar medium. So in the disk of the galaxy, we have stars, and then we have everything else. We have all this other stuff, gas and dust. The interstellar medium is all that other stuff that's not stars. All that other stuff, so the gas and dust, collapses to create these clouds, these molecular clouds, and then stars form within them. And when these stars form, they trap the composition of their birth environment and maintain it for much of their life, almost like a chemical time capsule. So the composition of a star, if you know how to measure it, will tell you about what the environment where the star formed looked like chemically. So if you look at an old star and you measure its composition, you're going to be getting a little sample of an ancient Milky Way. If you study a newer, younger star, you're looking at it in a recent form. So in that way, stars are chemical time capsules. And the interesting thing is that when stars form, their composition, again, is like a combination of a legacy of events that created elements before the star was formed. So I have a little movie showing like an example of all of this. So I'm going to go back. So let's imagine we're witnessing the birth of the first stars in the galaxy. It definitely didn't look like this, but let's just imagine. So the first stars would form. We actually don't think they even formed in a molecular cloud. We don't know how they formed. So, but they formed. If you think about it, the first stars would have no metals. Why is that? Because there were no stars before them to create metals. So these stars must have had only hydrogen and helium. These stars eventually die. They explode. They explode. There's a lot of animations to hand. Oh, there we go. They explode. They create these elements, right? These heavy elements. Oh, and then new stars form from those elements that were created by the first generation. So this second generation will have some metals. So if you look in the Milky Way and you pick out two stars and you see one that has almost no metals and one that has more metals, you could possibly come to the conclusion that the star without metals is older. And by the way, we're still searching for the first stars. That's a huge topic of research and interest, looking for these stars that have no metals, but we haven't found one yet, to my knowledge. And then finally, we have the third generation of stars that forms from the death of the second generation. You know, the second generation's dying, these supernovae are going off, planetary nebulae go off, elements are created, and the third generation has even more metals. So that's how the galaxy evolves chemically, and we can see it in its stars. So just to really, summarize all that, the composition of a star traces all the past events that came before it. So in this way, stellar chemistry is kind of like a star's genome, and it traces the ancestry of the stars that came before it. And finally, how do we actually measure a star's composition? Clearly, it's important, and if we know how to do it, we will learn a lot. To do this, we first start by collecting starlight through a telescope. and we disperse it through something like a prism. Technically, they're called spectrographs. And we disperse this light into a rainbow, and we study the rainbow. So the rainbow is called a spectrum. And the rainbow is not, well, it's more interesting when the rainbow is not just a simple rainbow, when it has these dark bands. And yes, so this is a two-dimensional view of a spectrum. So this is what our data looks like. And you can kind of turn that two-dimensional view into a one-dimensional view. That's how we usually study these things, but it doesn't matter. The point is, the spectrum has these dark bands, which are called absorption lines. And the position of the dark band tells you whether an element exists in a star. And then the darkness or the depth of that band tells you how much of the element is in the star. So if you were to like look at this star and compare it to this star, you would say this star has less iron in it, less sodium, less silicon compared to this star. So probably this star is older, right? It formed before generations of stars created a bunch of elements. Great. Okay, so how am I on time? Okay. So now let's talk about what we've actually discovered about our galaxy by studying the compositions of stars. So my favorite example of this, of a discovery that used galactic archaeology to understand our Milky Way, and an example of something that has benefited so much from what I'm going to talk about in a second, which is the big data era, is this example. So back in 1962, George Wallerstein, an astronomer, wanted to understand our Milky Way, and he wanted to study its stars. He picked 34 random stars. This is a big sample. This is a big deal in 1962. And he collected spectra of them, and he wanted to study their compositions. And he didn't really know what to expect, but he wanted to study all the elements and see if he could, learn something. So this is a figure from his paper. So each of these dark bands are a spectrum, similar to what you're looking at in the previous slide. And each of these are stars. So these are 6 spectra of stars, and then this is the spectrum of our sun. And you can see these features are associated with different elements: calcium, sodium, silicon, and the behavior of these features, the depth of the features, tells you how much of an element you have in the star. Okay, great. And he made a bunch of figures in his paper. He put on the Y versus X axis, he put a bunch of elements against a bunch of other elements. And he wanted to see if a star has this much of this element, how much of this element does it have? Like just comparing the elements. And in this figure in particular, something strange popped out to him. And this figure is a little bit confusing. So I'm just going to block out the axes and have just like some, qualitative words on top. So basically what he did is for all of his 34 stars, he placed them on this graph. On the x-axis, he plotted how much of iron the star had relative to how much hydrogen it had. And remember, iron is a metal, but hydrogen is not. So this ratio of how much iron to hydrogen the star has tells you about how many metals the star has. Did it form after many stars created metals? And so yeah, so if you see a dot over here on this side, it means the star had many metals, had a lot of iron, and over here it didn't have much. And then on this side, he plotted how much magnesium the star had relative to how much iron it had. And I'm surprised that this popped out to him, because when I look at this, I'm like, okay, I see a line, but he saw a lot of lines and he didn't think they were anything special. But what really popped out to him was he saw that these stars occupied 2 distinct tracks. One lower track, which corresponded to some of the stars in his small sample having less magnesium relative to iron. And then he saw another track of stars that had more magnesium relative to iron. So he saw these two tracks and he was like, whoa, this is a big deal. I think we're seeing something important, but we weren't sure at the time what it meant. It took us a little bit more time and the help of someone named Beatrice Tinsley to really understand what was going on. And I'm going to tell you what's going on in a second. But first, I want to show you how this plot has evolved since 1962. So we're now in the era of, we are now in the era of big data. We have surveys going online and obtaining data for millions, even billions, even tens of billions. I don't know if tens of billions, but billions for sure of stars all around the galaxy and beyond. So I'm just showing you some logos of different surveys that are online now. These are telescopes that are open every night that it's not cloudy, and they're pointing at stars and they're taking data all night. They just want as much data as they can. And I'm showing you a few really cool time lapses of a few of these surveys in action. So these are time lapses of, for example, we call this series of 4 telescopes the Very Large Telescope, the VLT. It's in Chile, and it's creating this survey, the Gaia-ESO survey, which is helping us get tons of chemical compositions of stars all around. Down here is another survey, the Gaia survey, that's being collected by this telescope here. And I wanted to also include this exciting telescope and survey that's going on. This is our most recent player in the field of big data. This is the Vera C. Rubin Observatory, also in Chile. It's conducting the LSST, which is not getting spectra, so we can't get compositions, but it's getting positions and brightnesses, tons of them. And each night, this thing is going to get, I think it's 20 terabytes of data per night for 5 years. So someone's going to have to deal with all this data. And it's not going to be me. But amazing, great. Okay, yeah, I just love these time lapses. Okay, great. So we have our figure from 1962. Let's see what it looks like today. So I'm going to show you what this figure looks like thanks to a survey I didn't actually show you. The survey is called Apogee, and I could not find a pretty time lapse for it, but it kind of looks, it's the same idea. It's a telescope in Arizona. It's collecting spectra of stars. Its aim is to collect 5 million spectra, and it's almost there. And so let's see how this plot changes when we start adding stars from Apogee. So I'm going to show you this plot build up in the order that Apogee has observed the stars. And we're going to see this plot change. And you're going to see, was Wallerstein onto something? Do those trends still exist now that we have so much more data? Or was it just a chance alignment of stars? And you might be wondering why things got rainbow. So we have, and then it's sped up at the end. It's because this was taking forever to make on my computer. So I kind of sped up there. And then I stopped it here because we actually have many more stars to add. But you can see the plot gets so crowded that I had to stop it somewhere. So the rainbow just tells us that there are a ton of stars. It's like a high density region. So the red means it's a really high density area. So you can see, just play that again. So you can see Apogee is collecting all these stars over time, and we're populating this figure, the same one that Wallerstein populated with 34 stars. And you can see this track here, this track here. You can also see some weird stuff here. Okay, what can we learn from this? Kind of already spoiled up there, but what we can see in this version, the 2025 version of this plot, is indeed we have some interesting structures in this plot. First of all, we have that higher track that Wallerstein saw, right? This is a track of stars with a lot more magnesium relative to their iron. And what we call this now, by studying the compositions and the motions of these stars in this population, we learned that the Milky Way has what we call a thick disk. So it's a disk of stars that are literally thick. So they're like chaotically orbiting the galaxy. They all have this weirdly high enhanced magnesium, and they're moving chaotically. So they occupy a larger height off of the disk. And this disk is older. And yeah, stars in this disk have higher magnesium and silicon and calcium as well. We also see this lower track, which are stars that don't have as much magnesium to iron as this track. And this is called the thin disk. So this is a population of stars that is younger, and it's not as enhanced. It's more depleted in these, we call them alpha elements, magnesium, silicon, calcium, and oxygen. And also what we can see in this 2025 view of the plot that Wallerstein could not have seen is this. What the heck is this region? It's kind of lumpy. It's kind of sparse, but like there's some weird lumps. If you watch the buildup, you saw there's like some clumps in here. What is that? That is what we call the galaxy's halo. This is the most, this is an ancient pot of stars that are swirling around our galaxy really far out, and they have very few metals. So they're all the way over here. If you remember from the way we designed the plot, stars over here have very few metals. So that means there weren't many stars before them to create metals. So these are some of the oldest stars we know of. And we also see these weird things called streams, literally streams of stars that are swirling around the galaxy. And those are some of these blobs over here. These are, if you were to study the motions of some of these blobs, you would see they form a stream in the sky. And these are dispersed satellite galaxies that the Milky Way ate up. So do you remember the LMC and SMC? It's a similar idea where these mini galaxies got gobbled up by the Milky Way. Now they're swirling around. Okay, how am I on time? Should I? 5 more minutes? Okay. Okay, let me think. I don't want to take too long. Maybe I can skip through this. We can understand how elements are made by comparing elements to other elements, just like Wallerstein did. But I wanted to finish off with saying we can't understand everything. We still have a lot of work to do when it comes to our instruments and our analysis capabilities. So I wanted to draw attention to, again, these strange elements in the periodic table. We still are trying to understand how they're formed. And what I'm showing you is, again, the same figure that I always show you. It's a very popular figure in galactic archaeology, where you have the ratio of iron to hydrogen, less iron here, more iron here. And then on this side, you have europium to iron. And the point is, if you count how many dots are in this figure, there are about maybe 300, 400. This is a state-of-the-art plot of high quality measurements of this element in our galaxy. So compared to the previous plot I showed you with magnesium and iron, we are really limited in our understanding of these heaviest elements, and also these two as well. But there are surveys that are going to be coming online soon that are going to help us understand, get more data on these elements, get more stars, and understand their compositions in these elements. And so what I wanted to finish off with is that even though we have these big surveys that are getting lots of data, measuring the compositions of millions of stars, there is still a lot of benefit from collecting your own spectra to study the more rare elements that I was just talking about, because surveys just aren't getting there yet. Okay, that's it. Yeah, so galactic archaeology helps us understand the Milky Way, and big surveys help a lot.
Thank you so much, Catherine. My brother would have really appreciated that. He is a paleobotanist, and I have to hear all the time how it really shouldn't be galactic archaeology. It should really be galactic paleontology. So he would have appreciated that shout out. If you can go.
Yeah.
All right. At this point, we will take questions. If you don't want to ask your question out loud, you are welcome to answer or to type your question in using the QR code above. I will repeat every question before Catherine answers it, and we'll occasionally go to online questions. But if you want to start.
Two questions. First one, do all galaxies have black holes?
Oh gosh, I don't know.
First question, do all galaxies have black holes in the middle of?
I would think so. Does anyone else know the answer to that?
Do you have a question or an answer? Okay.
Great.
So I think what we think right now is that galaxies, some galaxies have black holes, like our galaxies aren't necessarily like ingesting matter as some galaxies are. And you know, there are different types of galaxies. So we know a lot more about like our type of galaxies, so we live in it. So we're not but that's the extent of my knowledge. There's somebody else that was much more solid, but
Thank you so much.
So question number two has to do with periodic table. Because I studied chemistry at also very long.
Oh no, we have a chemist.
And what not really, but I don't remember how to write the periodic table when I studied it. But do they grow and do they partly grow because of the stars recodification and so on?
Yeah, so do we discover new elements, perhaps as stars continue to do this recycling of elements?
So new elements occur, then like the last ones and piece them together or whatever.
So could new elements occur
Yeah.
if you take like the two heaviest
Oh
ones?
gosh, that's such
fuse
a
them?
yeah, sorry. That's such a good question. Amazing questions. So like newly invented elements. I would think so, but I don't know. Wow, sorry, I'm so these are amazing questions. Yeah, so I think the reason the number of elements, oh, you want to say that again or?
Yes, so has the number of elements changed over time?
So I think the reason, so indeed, yes, the periodic table has grown, definitely, our view of it. But I don't think I don't think stars helped us discover new elements. I think it's more so like we're in the lab creating new elements there, or maybe running computations and understanding that, oh, this element should exist. And then we look for it in stars. So I don't think we've ever, because we need to know where to look. Because like when we get a spectrum, it's full as like those dark lines. It's like a mess. And so we actually don't know most of it. We don't know what it means, but we know the positions of a few lines. And so we're good with those. But yeah, I hope that answers your question. Those are great questions.
And a lot of them are probably active research questions.
Yeah, exactly. Yeah.
Okay, question?
so I know on the diagram, you're on people with like where or know that what and then some of the ones that like you said I did so kind of open up how they work or like labeled as so can you explain how carbon work is like
Yeah.
So how do neutron stars create these heavier elements?
Yeah, so we have, this is also an active field of research. We actually have, don't think they're here today. There are a few people who actually simulate this event. And they understand how much energy comes out. So I don't know exactly how a neutron star merger works. I know that like these two stars are coming together, they're orbiting each other. Eventually they reach a threshold where they combine. And then I'm looking at some of the grad students in the room who maybe have taken a class on this recently. But the point is there is an explosion, and this explosion releases, it basically releases these things called neutrons, which are, I guess you'd call them a fundamental particle, or, we have protons, we have neutrons. Neutrons are released due to this explosion, and then they collide with atoms. And that is the only way to make these heavier elements. It's not through fusion, it's through these atoms colliding with neutrons, lots of neutrons, to create these heavier elements. And these elements are highly unstable, so they decay. And that's how you create all these heavy elements. I don't know as much about the actual explosion, though. I don't know if anyone has any more thoughts on the explosion. That's a great question.
And it's the first neutron star merger was observed in 2017. So this is still like a large area of research. There have been simulations for a while, but the first one ever to be observed was in 2017. So just 8 years ago.
Yeah.
Okay, a question from online. Which generation of star is our sun?
It's the later one. It's like the third and beyond. We call it a Pop 1. Pop 3 is the first generation. Pop 1 is the most recent. So it's just somewhere in the mix of that.
Astronomers are not always good at naming things intuitively. Question?
Hi, Dr. Naya, thank you for your talk. I have a question about your manganese versus iron graph. So
Yeah.
for manganese, I'm sorry. For the iron, you plot it over hydrogen.
Yeah.
But for magnesium, you plot it over iron. Why do you not plot it over hydrogen?
Yeah.
So for those graphs, one axis was iron over hydrogen, and the other one was magnesium over iron. So why are they both not over hydrogen?
That's a great question. And that's asking, yeah, a really, really subtle question. So basically, if we were to do magnesium to hydrogen on the other side, we would kind of see just a 1-to-1 line, and it would maybe show like a subtle some structure, but it would be really hard to disentangle. Once we plot it relative to iron, we really see that structure pop out, because if we plot anything relative to iron, because all elements are made in stars, if we plot anything relative to hydrogen, because all of these elements are created in stars, everything kind of has the same trend. It just goes up, because stars are creating all of these elements. It's when you start comparing them to each other that you start to see these more subtle features, if that makes sense. Yeah, okay. Yeah, great question.
All right. So I was wondering what and the output.
Yeah.
What makes that
Yeah, that's
so what makes those alpha elements like magnesium special? Why look at those?
That's a great question. Okay, it's because this is kind of, I don't want to draw this out too long, because this is like when I was a grad student and I first started studying galactic archaeology, your question, we dedicated maybe 4 group meetings to just talking about this. So I don't want to drag it on too long, and I also don't want to oversimplify it, but the idea is magnesium is formed in one type of supernova, which comes from a certain group of stars, which are high mass stars. And these stars die. So the more massive you are, the shorter your life. So from when you form and when you explode, that time is really short. So older stars, like when you look farther back into galactic or cosmic time, you tend to see the output from massive stars first, because those guys died first. So the magnesium that they created is released into the galaxy sooner, faster. Whereas all the other elements take a lot longer to form. So by comparing magnesium and other elements that are created in these massive stars to elements that take longer to be released, we can start to see some of these interesting structures. So it has to do with the time scale at which they're created and released. Yeah, that's a great question. Yeah.
Thank you for talking about this. So you talked about like the halo stars that are out by the bottom.
Yeah.
But
Yes. Yeah.
Ooh.
Ooh.
What are
So what about the stars on that diagram that didn't fit into the halo or the thin disk or the thick disk? What are they?
Let's see. So up here?
yes,
Ooh.
yeah.
Yeah, so okay, I believe let's start with these. I think this is a guess. I think these might be very hot stars that so when a star gets to a certain temperature, like maybe 6,500 Kelvin, 7,000 Kelvin. I don't know what that is in Fahrenheit. So yeah, basically Celsius. Yeah, really, really hot. It gets really hot. The sun is 5,700 Kelvin. These stars are 7,000 and above. The structure of the star changes such that the elements. Wait, hold on. I think I'm getting confused. No. Sorry, this is right. The elements that exist in the star, some of them tend to fall inward and disappear into the interior of the star. And so when we study the star, it doesn't have really strong lines of those elements because those elements have actually sunken into the interior and we can't see them anymore. So I think maybe that's what these are. That's what I would guess. Okay, these up here, one guess I have, so they're super enriched in magnesium. Maybe there's a few things going on. Maybe this is again a guess. Maybe this star was really close to a supernova and it was like recently enriched supernova ejecta and it has like a lot of its ejecta. Maybe it's two stars in a binary system and one of the stars actually donated its mass to another one. So like it donated, but that doesn't really make sense though. I'm not sure. That's a great question. Honestly, like I would ask if I had some students willing, I would ask them to please investigate these stars because I'm not sure exactly what's going on.
Maybe that will have to be you one day.
Yeah.
Okay, I'm
Great
gonna do some of
questions,
the
yeah.
online questions. Does the sun consist of at least all metals that we've discovered on Earth?
Oh, does it, okay, so I guess that there's like, does it actually contain those elements? And then it's like, have we measured them yet? So when we study the composition of the star, of the sun, we can do it in two ways. One way is by like just getting a spectrum, like observing its light. And that's sometimes pretty hard to do because the sun is older and certain elements are really hard to measure in its spectrum. Another way we can study the composition of the sun is by actually studying the composition of meteorites, which we can actually hold in our hand and destroy and understand what they made of. And we assume that, right, has the same composition as the sun. I think we've measured a bunch of elements. I wouldn't be surprised if we haven't measured some of the really strange ones. But so the sun is like relatively, it's like middle-aged, I guess I would say. So it should contain the same amount of elements as other stars of its age. So if like we're talking about a really weird element, I would expect it to have it in there. Maybe we haven't. Oh, sorry. But yeah, like So there's a big field of research that studies whether the sun is chemically unusual. So we compare our solar system to others to see like, oh, do we live in a special solar system that's chemically unique and that's why we have life? And I think what we found is the sun does have some anomalies, like it tends to have some differences, but it's not dramatically different. So I would say probably if the element exists and it's in stars, then the sun would have it too.
Okay, another online question. Is the amount of an element in the universe determined by stars, and is it finite? So for example, with potassium, do bananas produce potassium, or do they do something with the amount that stars already produce to make it available to humans?
Okay, so I don't know about bananas a ton. So, but I do know that the way the element got into the banana, I know up to a certain point. That's a great question. So the element is produced in one of these explosions. It enters the galaxy, the gas, and then that gas collapses, and our sun happened to capture it, and so did all of the planets. And so the Earth was one of the things that captured the potassium that was created in some other explosion. And then in the Earth, I believe the elements were in the soil because the Earth captured them, and then the tree grew and it put the potassium in the banana. I'm not super sure beyond that level of detail. Did I answer the question or? Yeah.
Okay. One more from online. How old are the images of the Milky Way, that band of the Milky Way that we see? So how long does it take light from the center to reach?
Oh, okay.
This is when I tell my students to look away as I Google.
I know.
Okay, so 30,000 years. Thank you, Fred.
Thank you. That's a great question. I know I have a few numbers in my head. Like I know that the close nearby galaxy I showed you was 400 million light years. The closest star is 4 light years. But I forgot to memorize the center.
All right, I think on we'll do 2 more questions. How did you get it?
Yeah, I feel like yeah, growing up, I don't remember the first time I got excited about it, but my parents bought me this astronomy atlas. It was like one of those giant books that have just flip through pages of like artist depictions of Saturn and the galaxy and like black holes. And I remember I would just read those over and over again, and it just really captured my excitement. And when I knew I wanted to do it was in high school. I had a physics professor who was also an astronomy nerd, and he would host star parties exactly like the one we're doing in a bit. And he took us out to the mountains and we observed with him, and we saw, like, I remember seeing Saturn for the first time and seeing the rings. And I was like, I can't believe we're actually seeing like planets beyond, let alone nebulae and galaxies. Think that I think that was probably how it happened. And then I kind of never looked back.
Okay, our final question.
Humans have learned to take like even near galaxies to reach us.
Yeah.
Doesn't that mean that the vast majority of the galaxies that we can see are technically long dead already?
So since it takes light so much time from other galaxies to get to us, does that mean that all of the galaxies that we see are actually dead?
That's a great question. Okay, I think that this is a question I've been asked in my qualifying exams in grad school because it involves thinking about how long light takes to reach you and also the lifetime of a galaxy. Okay, let's think. So, okay, let's talk about the nearby one that I know is 400 million light years away. I think it will probably live many billions of years. And I don't think it's on the end of its life. So that guy is definitely still around. But your question was most of them. You're nodding, Danielle? Are- Yeah. Ooh, right. Yeah. Yeah,
So
that's a
many
great
things
question.
can happen, and also depends on what you mean by dead. So galaxies, they always still exist, but they might not have any active stars, or maybe they're not making new stars. Maybe they've merged with another galaxy. So even just what dead for galaxies mean is up for debate. Okay, I'm going to answer one more question online. This one is how to counter Trump and his cronies sabotaging crucial scientific studies, defunding and canceling projects, destroying satellites. This is up to you all. So talk to your representatives. If you care about this, if you think they're doing a great job, tell them you think they're doing a great job. If you wish that they wouldn't defund science, tell them that they're supposed to work for you. So that's how it's supposed to happen. All right, now the reason. All right, now the reason why I know you all come is for our wonderful giveaway with the raffle. How this works, I'm going to swap spaces with you, is that there's a seat number on the back of your chair. This is for testing assignments, but you don't have to take a test. Instead, you get the chance to win either a tote bag or a mug. So if I call your seat number M17, C9, C9 as in cats. You? All right, mug or tote bag. You can come up and get it later or now. You don't need to leave your seat. But you can take one, mug or tote bag. All right, one mug claimed. K16, F11, F4, H13, G6. All right, mug or tote bag. All right, you're welcome to get it as you leave. Okay, where did I leave off? G11, did I do that one? All right, mug or tote bag. Bag. Okay, we have one mug left. Is anyone in E11? Okay, what about A9? No. All right, let me refresh for more numbers. Okay, what about F4? No, I did that one. What about, oh, F4, okay. All right, thank you all. And it is still clear, so we can go up to observe campus levels on the 5th floor. I don't know exactly where they are, if they're right outside the building or if they're on Low Plaza. But I'll be up in a minute. There should be a couple of telescopes right outside. Thank you all so much for coming. Let's give another round of applause to Catherine.
Great questions.